In the last video, we were studying damped oscillatory motion, and we said that whenever an oscillator is placed in an external medium, you take an oscillator, place it in an external medium, and what happens is it does not continue to oscillate. Slowly, the oscillations die out. The amplitude goes on reducing. The amplitude goes on reducing. So, what is happening? What is happening is that the initial energy that you gave it is losing its energy somewhere. It is dissipating or spending its energy. Where is it dissipating or where is it spending its energy? It is spending its energy in overcoming the resistive motion that the medium is giving it. So every medium will have this property of opposing motion inside that medium. It might be through friction, it might be through viscosity. If you take the air medium, air will have some kind of viscosity which does not want motion to go on forever. If you place the same simple pendulum in vacuum and leave it, it will go on forever, infinitely. Why? Because there is nothing that is stopping its motion. But in air or in water, it will get damped. So in damped oscillations, we saw that the two main characteristics are that the amplitude goes on decreasing and the energy also goes on decreasing. Now, in the previous video, we studied the differential equation of damped oscillatory motion. What was the differential equation? M d2x by dt squared, this is the net force, plus r dx by dt, this is the resistive force of the medium, this is the external resistive force, and kx, which is nothing but the restoring force of the oscillator. This is a property of the oscillator, this is a property of the external medium. Together you add these three, you get the differential equation of damped oscillatory motion. Then we assumed a solution. Saying that x may be of the form a e raised to minus alpha t, alpha t, and then we got this alpha, and finally when we solved it, we got x of t is equal to a1 into e raised to this entire term minus r by 2m plus something into t plus a2 e raised to some term into t. Today what we are going to do is, we are going to take three different cases and we are going to try and study them. Because when you have damped motion, when you place an oscillator in a medium, three kinds of motion are possible. When you take an oscillator and suspend it in vacuum, or keep some harmonic oscillator on a frictionless table in vacuum, no friction, no viscosity, nothing. Take a simple pendulum, tie it to a rigid support, place it in vacuum. There is no viscosity. In that case, all that we did in the previous module applies and those oscillations will never die. But whenever you place it in a medium, three things might be possible. One particular motion is called overdamped motion. What does it mean? We'll come to it in a moment. Second type of motion is critically damped, and third type is underdamped oscillatory motion. What do all these three mean? Let us try and understand. The first case that we are going to study is, what if r square was greater than 4m? Or if you look at the solution, what if this term inside the square root sign, this term is greater than this term? So that's why I have written, if r square is greater than r square by 4m square is greater than k by m, what does happen? What does this mean physically? Physically, this means that the resistive force or the damping force is greater than the restoring force. Damping force is the force that doesn't want the oscillator to move externally, and restoring force is the internal property of that oscillator which keeps it moving. If this force is greater than this force, let us look at this bracket. We have e raised to something into t, right? Let us just look at this bracket. First term is minus r by 2m plus square root of r square by 4m square minus k by m. Similarly, second term is minus r by 2m minus square root of r square by 4m square minus k by m. You have these two terms in the brackets. Now, this term is negative because r is positive, m is positive, so this term is negative. This entire term, if this is greater than this, let's come to this one first. This is negative. If this is greater than this entire term becomes positive. This entire term becomes positive. And when you add two minus things, suppose this is minus 3, this is minus 2. Minus 3 minus 2 becomes minus 5. So the entire term becomes negative. This whole term should become negative. Here, this is positive, this is negative. Second term is positive, first term is negative. But which is greater? This term is greater. This term is greater. So for example, if this is 3, this will be 2. So minus 3 plus 2 will again give you a negative number. So again, the whole term together becomes negative. Okay. How does this term become negative? Because this term is greater than this term. This is greater than this term. Okay. See, very simple. Let's assume this number is 3. Let's assume this number is 3. So what is this number inside? Inside the square root, this is 3 squared, right? R by 2m squared. 3 squared is 9. 9 minus some positive number. K is positive, m is positive. So K upon m has to be positive. So 9 minus something will always be less than 9. So this entire number is less than 9. So this entire number has to be less than 3. So this term will always be smaller than this term. Always, always, always for any kind of oscillating system. Therefore, this term becomes negative. Now look at your solution. Your solution will become x of t is equal to a1 e raised to minus something into t plus a2 e raised to minus something into t. This is negative exponential function. This is negative exponential function. Addition of both will give you a kind of graph which will again be a negative exponential function. So let's say this is the time axis, this is the displacement axis. Let us assume that this is the mean position. This is the mean position, okay? This is x is equal to 0 or some kind of mean position. So the graph that you will get will be something like this. A negative exponential curve. What does this mean? This means in real life or in physical terms, what this means is once this particle is displaced from the mean position, that means you take this pendulum, you displace it from the mean position and you let it go. In this particular case, what is going to happen is the resistive force is going to be so great. The resistive force will be much greater in comparison to the damping force. And because of that, what will happen is it will come back to its mean position very slowly. It will take a long time to come back to its mean position. Imagine placing this simple pendulum in some very thick liquid, not even water, something even more viscous, some kind of a thick oil, and then you allow it to swing. You will see that the pendulum comes back with great difficulty to its mean position. It won't come back quickly. Now air is very less viscous, so you see it coming back very quickly. But in reality, when you have a very viscous medium, it will take a long time to come back to its mean position. This particular case is called as overdamping. Overdamped motion. Overdamped motion. So in overdamped motion, your external resistive force is greater than the restoring force. External resistive force is greater than the restoring force. Once you displace the oscillator from its mean position, it comes back to the mean position very slowly and there is no oscillatory motion, because oscillatory motion should be up and down around the mean position. There is no oscillatory motion in overdamped motion. That is the first case that we studied. Now let us look at the second case. I'll write it here. Let us look at the second case. If r square by 4m square is equal to k by m. If r square by 4m square is equal to k by m. Or in other terms, you can say r square is equal to 4m. In this case, what you get is the restoring force. The restoring force is equal to the damping force. Is equal to the damping force. The restoring force is one that does not want motion. The damping force is one that wants this oscillatory motion. Now you have both these forces balancing out. What do you think is going to happen? Again, no oscillations are possible. No oscillations will be possible in this case. But in this case, what will happen is, see this term, this entire square root thing will become 0 because this and this is equal. So this term only remains minus r by 2m. Here also what you get is only minus r by 2m. So your solution will become x of t is equal to a1 e raised to minus rt by 2m plus a2 e raised to minus rt by 2m. But because e raised to minus rt by 2m is common, you could write this as a1 plus a2 into e raised to minus rt by 2m. But there is a problem. What is the problem? Mathematically, when you have two similar roots, this becomes one constant, but one differential equation of second order differential equation should always have two constants. So if you study the theory of differential equations, we won't get into that here, but when you study the theory of differential equations, the way to write this solution is, what we will do is, we write this as a plus b into t multiplied by e raised to minus rt by 2m. This is how you write it when it comes to differential equations. How will this graph look like? You might say, well, again it is an exponential, falling exponential. Yes, but there is a slight difference. This is your mean position. Now, after displacement, it will come back in a very short time. Your particle is displaced, but now it will come back to its original position in a really short time. In a very small time, it comes back to its original position. And this entire case is called as critical damping. This is called as critical damping. Okay. Now, where do we see this over damping and critical damping in the real world? Do we ever see it in the real world? Yes. Over damped motion is most commonly seen in a damped oscillator. In a door dampener. You might have seen in many offices there is some kind of a dampener attached to the door. You see some kind of black object at the top of the door. So see, this is the door, this is the hinges. You open the door. Once you open the door, you leave it open. If there is a breeze going, or because of the hinges, what is its property? This door wants to go back to its main position. And if there is a large breeze, it will suddenly go and bang against the door frame. So it comes and bangs against the door frame like this. Then it comes back again a little bit, again bangs, a little bit less, again bangs, and then stops. What happens is, repeatedly, your door frame gets destroyed, and this noise is also not very pleasant. No one likes to bang doors. What we do is, when this door is open, now this door wants to go back to its main position, but it will not just stop there. Because of its force, it will go beyond. But it is restricted by the door frame, that's why it comes back. It hits and comes back and bangs again. In order to avoid this, what we can simply do is we apply a dampener. Now imagine I am holding my hand. Now somebody pulled this back. Now it wants to go this way, but now I am holding it. Now it will go slowly, 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 and stop. I have stopped its motion, or I have damped its motion. That is why this particular case is called overdamped motion. You damp it, not just little bit, you damp it quite a lot. It will go slowly. You might observe those doors go very slowly, but they don't bang because there is a dampener involved. So this kind of motion is called overdamped motion. Now, let us look at the second kind of motion, which is critically damped. This is much more common, and this is something we look at very often around us. Where do we see this critical damping? See, critical damping is first of all seen very commonly in shock absorbers inside vehicles. If you have observed shock absorbers in any kind of two-wheelers or cars, the shock absorbers are basically springs. Shock absorbers जो होते हैं वो springs होते हैं, isn't it? So जब कभी आपकी गाड़ी किसी गड्ढे पर से जाए या किसी स्पीड ब्रेकर पर से जाए, your vehicle crosses a pothole or it crosses a speed breaker, suddenly that shock absorber is displaced from the mean position. Let's say its original length was this much. Now suddenly it became this much. It got either elongated or it got compressed. If it goes on a speed breaker, the shock absorbers are compressed. If it goes through some kind of a pothole, the shock absorbers might suddenly get elongated. It is displaced from its mean position. Now, this is not its natural position. The vehicle ride is comfortable when the shock absorbers are at a particular length. Now, this is displaced. What do I need? I need this to come back to its original position in the least possible amount of time. See, if it comes back late, then it is not that comfortable for the rider. It should come back quickly, and it should not come again, it should not start oscillating again. आपका शॉक एब्जॉर्बर मान लो सडनली इलोंगेट हो गया, वो वापस अपने मेन पोजीशन पर आना चाहिए, जल्दी से जल्दी आना चाहिए, और उसी के साथ उसने आकर ये ऑसिलेशंस नहीं करने चाहिए, अदरवाइज इट इज नॉट कंफर्टेबल. व्हाट यू वांटेड इज टू कम बैक टू इट्स मेन पोजीशन क्विकली and without further oscillation. In that case, you use critical damping. So this critical damping is something that we introduce in a shock absorber by various means in order to give comfort to those who are riding that vehicle or driving in the car. Now, there are other uses of critical damping as well. Slightly, you might not perhaps associate this with oscillations, but still try and follow my reasoning. Try and follow what I'm trying to say. There is a scale. There is some kind of a circular scale, and you have a pointer over here. Where do we see this kind of arrangement? This is a scale. Okay, this is a scale. We see this kind of arrangement in a weighing machine. We see this kind of arrangement in the analog speedometers. You remember we had speedometers in our vehicles earlier. They were analog, not digital. So you could see that going up. Now imagine you stand on a weighing machine. you stand on a weighing machine and your weight is 50 kgs. 50 kgs is marked over here. Okay. What you want is this should go slowly and stop at the 50 kgs. You don't want this to go here and then keep oscillating, isn't it? You want it to settle down to this position and you don't want it to slowly go. Imagine you stand on the weighing machine, you stand for 10 seconds and slowly it goes. It's very frustrating. You stand on a weighing machine for 3 seconds, you should be able to, the pointer should come and wait somewhere, should indicate some kind of a reading. This thing should happen quickly, and so here we use critical damping again. Perhaps you might not associate this with oscillations, but again this is a use of critical damping. Even in your speedometer, let's say from you just started your vehicle, your speed is 0, and now you suddenly get a very free road and you are at 40 kilometers per hour. This transition, your speedometer should be able to show you quickly and accurately, and it should not go beyond 40, like 50, 40, 30, 40. There should be no oscillation. It should go on 40 and stop there. So in all kinds of analog meters, whether they are voltmeters, ammeters, weighing scales, speedometers, every place we see critical damping. So these are two very important things. Overdamping, when the resistive force or the damping force is greater than the restoring force. And second is critical damping, where the resistive force is equal to the damping force. But in both these cases, there are no oscillations. Oscillations by definition are about a mean position, there should be to and fro motion. No oscillations here, no oscillations here. Then why are we studying damped oscillatory motion if there are no oscillations? There are damped oscillations. That is something we'll look at in the next video. Alright, we'll stop here.